This is problem 98 from chapter 12. This is another projectile motion problem. I have a few more examples of projectile motion problems that I want to give you, but hopefully at this point you are starting to get the hang of how things work. So I'm going to go through the next example problems rather quickly, and if you feel confident in solving these problems now, you can give it a try on your own and then just come back and check your work afterwards. So this is problem 98. We have a tennis player hitting the ball with an initial velocity of VA. This is in the horizontal direction. It just clears the net at point B, which is 3 feet above the ground. And we also want to find the distance where the ball hits the ground. However, they're measuring the distance from the net. In my diagram, I've drawn it so the initial velocity is going in the right direction because I think it's easier to work this way, and it doesn't change any of the answers. So we have the ball leaving here, we have 21 feet between the player and the net, and a distance s between the net and where the ball hits the ground. So we're going to break this problem up into two different sections. First, we're going to look at the initial velocity that you would need in order to just clear the net. So that's going from A, where the ball is being hit, to B, which is where it just clears the net. So that's going from here to here in the initial diagram, which is going to be from here to here on my new diagram. And because we're only going to point B, I've called this delta T AB, so that this is just the time between when the ball is hit and when it clears the net. Delta S goes from point A to point B. The velocity is in the horizontal direction. And then we have the acceleration vector pointing straight downward, and we multiply that by 1/2 and delta t squared. In the horizontal direction, VA times delta t has to be equal to 21. That gives us one equation. The other equation comes from looking in the vertical direction. If the ball is hit 7.5 feet above the ground and the top of the net is 3 feet above the ground, then the displacement in the y direction is 4.5 feet. That must be equal to 1/2 of a times delta t squared, which is 16.1 times delta t squared, and solving for that, we get delta t. You can take that delta t and equation 1, which we have here, and you can solve for the initial velocity. You should find that to be 39.7 feet. Then, to find the distance between the net and where the ball hits the ground, we're going to look at a new diagram, and I still want my initial point to be A because I did not find the velocity that the ball has at point B. So if I was going to go from point B to point C in order to draw my vector diagram, I would need to know the velocity at point B. So it's easier just to go from point A to point C. So now the velocity times delta t, that vector is still pointing in the same direction, but it has a different length because now my time is from A to C. Similarly for this vector, it's still pointing straight downward, but I changed delta t to be from A to C, so the vector is going to be longer. Now delta s points from where the ball was being hit to where the ball lands. Again, I'm going to look in the horizontal direction, and VA times delta t is now equal to 21 plus s. And my acceleration vector, which is pointing straight downward and being multiplied by 1/2 and delta t squared, is equal to 7.5. From this first equation here, well, I can put in the 39.7 that I just found. I still have two unknowns. So then I look at my second equation, which came from looking in the vertical direction. I can solve this for delta t, and then I can take that and put it into the equation that I have up here, and that will allow me to solve for s, which is 6.1 feet, and that concludes problem 98.